So we're on with lecture 26, where I'm planning now just to complete, even though that 25 ran over, I still have a factorization to do for this polynomial, and I still have to tell you what's good about that very particular polynomial, the minus 1, 0, 9, 16, 9, 0, minus 1, and what's better about the one that leads to, so there's the 5, 3 I'm dealing with here, and then the 9, 7 that is even better. Okay, so this fellow, so this is our P naught, and I factored it. And the remarkable thing is, and that's why it's so good, that's why those particular numbers, I mean, the zeros, everybody remembers the zeros had to be there. Zeros had to be there for the perfect reconstruction part. But now we've got freedom on these 9s and minus 1s and so forth. But so we use that freedom to get whole lots, and I've, instead of e to the I omega, e to the j omega, I just wrote z. Just to make it simpler, shorter. So z equal minus 1, of course. This is the z plane. And this is the omega circle, you could say. The unit circle, the z equal e to the j omega. So there's the, and here is the important point where we're seeing 4 zeros. So 1, 2, 3, 4 zeros at the big point, z equal minus 1. So that z equal minus 1 is omega equal pi, and that's where we want low-pass filters to be 0. Why don't we just say, okay, great, we'll use these coefficients for P naught. We couldn't have more zeros than at pi than that gives, then we couldn't have a, I mean, it has nothing, no waste as far as zeros at pi, but, so why don't we just use this filter as the product filter, factor it, do whatever we like? It hasn't got this requirement satisfied for that we needed in the perfect reconstruction. So if we tried to invert stuff here, we would get into IIR filters. Well, big debate, still raging. Actually, I refereed a paper this morning where the guy suggested these filters, and then he said live with IIR in the reconstruction step. Well, the paper had been rejected by the main Wavelets journal for that reason, probably. But still, there was some good ideas, so he's rewriting it.
Wouldn't that give an infinite delay?
It would give an infinite delay if we did it exactly. So it's like Butterworth filters are the continuous analog, famous. So they're quite efficient, but you got to deal with infinity somehow. Okay, here we don't. Here we're really staying finite. So we've got this extra factor. So this has the roots of this, of course, everybody sees are these 4, and the roots of this remaining quadratic that we needed to toss in, or there's one root here and there's another root here somewhere. Yeah, we could locate them. It's not hard to. If it's a quadratic, we could find its roots for sure. Okay, so now what's the deal? We're going to factor this into. We're factoring this whole thing into H naught times an F naught. So we'll put whatever zeros we want with H naught, and we put the others with F naught. So what should we do? Well, we don't want to put all these in H naught and those two bad guys in F naught. That would wipe out F naught as any use at all. So then a natural idea, well, what do you think? we could put two of these zeros in H naught. So you see what I mean? We could let H naught be, this could have two of the zeros, and then maybe one of the other pair. So A plus B, Z1, Z inverse, whatever it would be. I should know those numbers anyway, but what the heck? You see what I'm saying? You see the options. And then F naught would have the other two zeros of P naught. The whole thing is P naught. So we've got those four zeros and then the linear, one more zero, the linear term. So that guy times this guy are what produces the quadratic. Is that a good idea?
Wait, doesn't that divide it evenly?
Doesn't who?
That divide give us filters of even length.
It does. And so this would, and what length would it be? Good, exactly right. What length would it be? 4. So this would produce a 4-4 filter bank, and it would be the Dobeshy, most famous of all filter banks, of all wavelet constructions. It's what she became famous for, finding these. So she did this balanced factorization where one of these went with analysis and the other went with synthesis, and that balancing made her filter banks orthogonal, separately orthogonal, but not symmetric. Not symmetric, because this is nice and symmetric. This is a 1-2-1, but this thing is somehow it's a 1 alpha or something. It makes it unsymmetric. So this is 4-4 Dobeshy's orthogonal but non-symmetric. 4-4. Okay. So that's quite an important filter, very important filter, but not symmetric filter. So it doesn't get used in image processing. So how shall I change things to make it symmetric? Put them both on one side. Put them both on one side. So let this be the F naught, and you see that's going to give us the 1. This gives us, with this square there, this is then the 1-2-1. And put the whole other factor, -1, 4z inverse, minus z to the -2, put the whole quadratic over on this side, and if we multiply that out, that's what gives us the -1, 2, 6, 2, -1. Now, we knew this. We knew that that one factorization of P naught was this. So, again, the new question was, why is this P naught of special interest? And what's the answer? Why this P naught and not some other numbers? Because for an unexplained but perhaps reasonable cause, we like these. We like the fact that it has 4 0. We like the fact that it has a lot of zeros at -1. Okay, so if you were Dobeshy, what would you do next? Going up the line, what would the next P naught be that you would then factor? Okay, so now we're really inventing the whole Dobeshy family of filters. What would the next P naught be? Let's see. We want 6 zeros, right? And then we're going to have some loser. Quadratic may not do the job, because if I go up to 6 zeros and then try with a quadratic, what will happen? I've only increased the degree by 2. I'm popping something new on the ends, but Those are zeros. Yeah, they have to be zeros, right? Because I need zeros in all. So I have to go up by 4. That's the thing. I have to go up by 4. So the next will be up to degree 10 with 6 zeros at -1, which is pi, and a 4th degree bad factor. I'll say bad because we'd be happier if we didn't need it, but we do. Okay, and that would give us another step up. But let me take the next step, because that's where 9,7 comes up. The next degree will be 14 with 8 zeros at -1 and a 6th degree bad factor. So can we draw that situation? Let me redraw the unit circle, and let's just imagine. Could we construct this thing? Well, with a little you see what determines this 14th degree polynomial? Just have we got the picture straight? What determines that 14th degree polynomial? Well, this determines a good bit of it, having 8 zeros at -1, leaving us with a 6th degree factor but what determines that? Inserting those odd zeros. That's right. The requirement of odd zeros is what determines the remaining factor. Odd zeros, I mean these zeros and the next one at -7 and so forth. Or whatever, wherever it's centered. It's probably centered up further along. Probably the center will be at z to the -7 when I'm up to degree 14. Okay, so we could do it. And we could factor it. And that's what the FBI used. I don't think they did the factorization, but they used the numbers. And I just got those numbers by email. I could communicate them. Sorry? Yeah? Yeah.
Isn't there a way to factor it and to automate it to do that?
To automate, yes. So what do you want to automate? The construction of P naught?
Right.
And then the factorization, right.
So then you could automate, you could just generate the whole family.
Right. Yes. So there are nice formulas involving binomial coefficients that produce these P naughts, because those are nice. Everything's nice about those things. The factors are not so beautiful. Well, we got 8 beautiful factors here, 8 times, but then we have 6 more factors to account for, and probably, let's see, probably there's a couple of real ones, and then there's maybe something and its complex conjugate and its reciprocal, and it's something like that. Those are the 6 factors, 6 roots, which only MathWorks, would pay them to find those roots. So, which they don't actually do. In fact, here's an interesting point. If you give even this polynomial, did I mention this before? Because I'm a fan of MATLAB, but I was disappointed when I put in that polynomial, which has 6 roots. I mean, it's an expensive program. It can find roots of a degree 6 polynomial. Well, it didn't find these 4 roots very well at all. It found 4 roots that were in a little square around -1. And visibly not right. I mean, imaginary parts and everything. And then you put the 14th degree one in, and you're really missing by a bit. So it shows that the old, the classical problem of roots of a polynomial, when you have multiple roots, is very ill-conditioned. I mean, this is low degree. And actually, maybe I just tell you one moment. I had a really good PhD student a few years ago who computed, right, we use the formulas and use roots to compute the roots. And when you go up higher degree, these roots are like, it seemed like they were lying on a circle. Seemed plausible anyway that they were, and these ones, or at least close, very close to a circle. And yes, sure enough, he found the circle that they were approaching, and quite beautiful identity. So they're very special polynomials. But what's the 9-7? Just tell me how to produce 9-7 out of these 14 roots. So I've got 8 and 6, 14 roots. I'm going to put 9 of them. No, I don't want 9 and 7 roots. Why do I not want 9 and 7 roots? Because 9 coefficients, I only want 9 and 7 coefficients. So the degrees are 8 and 6. Yeah. So this has 15 coefficients, you could say. But degree 14, I'm going to factor into F naught and H naught, and this will be degree 8, and this will be degree 6, with 9 and 7 coefficients. Right, good. Okay, so what shall we do? What shall F naught be? Yeah, take half of these and give 4 and 2. And now it's clear how we would do the 4 and 2. Because we don't want to separate these 4 friends, right? Because if we try to separate them, we're going to spoil. I mean, by keeping them together, we keep the polynomial real, so it'll have complex pairs as roots, and we even keep it symmetric because we're keeping these with those. And then the other one the 7 will have 4 roots there and these 2 roots. Good. So there you go. That's it. And so everything is explained. We can see that there would be formulas, and the book actually gives several equivalent formulas for those P naughts. There won't be formulas for the roots, but we can compute them. We have really not developed very fully why these zeros at pi are desirable. And actually, that comes up also in the continuous time situation. So we'll tackle that. Yes. I said something about being orthogonal, right? Yeah. What does that mean? That means that the H naught is the flip, because it's like transpose, of the F naught. So I can tell you, so I'll put down what these numbers are. The H naught coefficients happen to be 1 plus root 3, 3 plus root 3, 3 minus root 3, and 1 minus root 3. And the F naught coefficients have them in the opposite order. 1 minus root 3, 3 minus root 3, 3 plus root 3, 1 plus root 3. And if you multiplied that polynomial, or the polynomial of that coefficient times the one with that coefficient, you'd get my friend P naught again. Those are the two cubics that multiply together to give this guy. And notice, you see how one is the flip of the other? One is not the flip of itself. So they're not symmetric. Bad point for image processing. But one is the flip of the other, so that H naught is the transpose, you could say, of F naught. And we would see similarly that H1 is the transpose of F1. So what does that mean? That means that the analysis bank is the transpose of the synthesis bank, which is what orthogonality is. That analysis times synthesis, but the synthesis is A transpose, is the transpose of analysis, is the identity. That's orthogonal. That's what orthogonality means. Yeah, so, and this is called spectral factorization in the EE literature. So spectral factorization is the factorization where you split these. You keep the ones in the unit circle on one side, you keep the ones outside the unit circle on the other side, and that gives you orthogonality, but it kills symmetry. Okay, that was a quick response and not full detail. I guess I'm ready to tackle to pause in the heavy polynomials, factors, numbers everywhere, and just take a step back and look at the big picture. Because it's that bigger picture that's important to understand where wavelets have a part, where they're valuable. What is it? And it's associated with this word multi-resolution or the word multiscale. That I want to bring out here. And I may not complete, I won't complete everything that's to be said about wavelets, but the calendar allowed for that. Okay, multiscale, multi-resolution. Let me take the word multiscale first. If I go to a conference about solving problems of physics, and I would expect the same in the applications at the lab, the biggest headache in the tough problems is wide variety of scales all contributing, which we know in turbulence, for example, which we know is a tough problem, and it's a multi-scale problem. We've got big eddies and smaller eddies and smaller eddies, and they're all, and how are they connecting? In physics, in nuclear physics calculations, we've got large distances and we've got minute distances. All sorts of problems are producing this, and of course the difficulty is you cannot deal with the fine scale and the coarse scale in the same way. If you're going to resolve the fine scale, then and not change your method, then you're going to do infinite amount of work on the coarse scale that was totally inefficient. Everybody understands this difficulty. That somehow we need to deal with multi-scale problems, recognizing that we need a multi-scale algorithm. We need an algorithm that computes something at the fine scale and looks at the correction it produces to the large scale, but some terms are not important, and we got to know which are important and which are not. Okay, that's my sermon on multi-scale. I'm just seeing that everywhere. Okay, and multi-resolution is a way of dealing with it. Okay, so what is multi-resolution? Multi-resolution means that we are, really multi-resolution is, so let me, multi-resolution really is somehow taking my function and writing it as a sum of functions at different scales. Maybe I just write it, sum fj of x at scales, say, from 0, well, in principle, infinity, but in real calculations, not. So what's fj? It's a function at scale j. It's maybe some so there we might have I'm sort of creating things at scale j. So at scale j, what do I have? I have maybe some function. And what does it mean to have, I need to distinguish these scales. If it has a 2 to the j t, that's something at scale j for me. You see, if I have a function of t, a function of 2t, that's really what I want you to think about. Is if I graphed a function of time and a function of t and a function of 2t, what would the two graphs look like? Suppose, well, let me take a really simple graph for my own reasons. Suppose the graph is like that. So this is like picking it's just a square wave. If that's phi of t, what's the graph, say, from 0 to 1? What's the graph of phi of 2t? It's scrunched, right? We don't use that technical term in wavelet theory, but that's exactly right. It's scrunched to a half, right? Compressed or whatever. So it's on this finer scale. So this, and if I do it j times, then I'm at 1 over 2 to the j. So this is, and now, so that function, but I want that function and its translates, because if I'm just using these single functions, that won't do. So really, I'm going to build in functions of this. So I have j as a scale index, but I also need a k as a shift index, because I'll have a so fj of x will be the stuff at scale j, which will be a sum over the k index with some coefficients a, j, k, I guess I need. You see, I'm needing two coefficients here. Position, this is k is giving me somehow the center, the position of the function, and this is giving me the scale. So my functions have a double index. We're in a time, position or time, depending whether we're in space or time problem. So we have a sort of a time scale picture, where it happens and what scale it's on. And that would be, so this would be a term at scale j, and now we have another term at scale, at every j, we have these terms. Okay. All right, so I'm still looking at trying to look at the big picture here. Well, yeah. So here's really the big picture. That we want to take our function and separate it into things at different scales. Let's take that Haar example. The Haar example would be a good one. All right. Just for vectors, because we're doing filter banks did the same for vectors. Do you see that? Do you remember those filter banks? You remember that we had, right? You remember that we had this sort of structure. So these were something at what at a coarse scale, right? They only had it every 16th gave a number, and this was a little. So these were 16 was the scale there. Here we had an eighth. Here we had a fourth. Here we had a half. The output from a filter bank has this multiscale aspect. This is fine scale down to coarse scale. And in continuous time and in our analysis, we could imagine the thing going forever. So that's really what wavelets, continuous time wavelet stuff does. It imagines this infinite sequence of scales to get the function exactly right. And filter banks imagine a sequence of 4 or 5 scales to get a vector exactly right. I didn't say, how would you invert, just if you allow me to go back to filter banks for a moment, how would you invert this iterated filter bank, this tree, filter bank tree? How would you invert that? Because this is like the analysis, this is the analysis tree, where we got to the stop, and now how do I invert that? I'm reverting to the previous lecture just because. Take the top 2, right? Exactly. That, and then let this guy come in here, and then let this guy add in the new details, and add in the new details, and you get X back with delay. Yeah. So just so it's clear that iteration everything remains very easily inverted. If we know how to invert one step, then we just concatenate those. Right. Okay. So the idea will be in continuous time that the mathematics would allows for infinite sequence of scales, and allows then to deal with functions. And so you might say, wait a minute, this is realistic, infinite is not realistic, but infinite is a very good guide to 4. I mean, in the same way that calculus gives you a very good guide to what happens a little later for a function. But you'd need the whole infinite Taylor series to say exactly. Similarly here, if we know what's going on in continuous time, then, and we know these wavelets and these constructions that are like ideal multi-resolution. Maybe that is, by using the word ideal, I'm sort of saying not executable because involving infinity, but still very clear as a model. Yeah. So in a way, the wavelets are ideal filter banks where you iterate forever. Yeah. How does the phi relate to anything? That's right. Okay. There's a function phi here, and there's a function w. Okay, so now I'll get down to brass tacks here. We've got 2 functions in this wavelet world. One is phi. The other is, well, I broke new ground in the book by calling it w. It's the wavelet. And then the usual name has been that, but I'm, with most people in the world, not too blessed sure how to say that thing. So, or even at a certain age, your eyes on the printed page don't easily distinguish those. So, well, that's my little contribution to the work. So this is called the scaling function, and this has to do with the averages. So this scaling function has, and this is the wavelet. So this scaling function, now we've got that inverse thing. Let me tell you what are phi and w for har. For phi and w for har. So the har example, so there are 2 functions associated with, because we got 2 channels. We got a low pass and a high pass. So this is sort of going to be a low pass function, and this will be a high pass function that gives us details. So wavelets, scaling functions, this is associated with averages, and wavelets will be associated with details. So this isn't complete yet here. You said, what's that phi up here, because I just produced it. But actually, I ran out of energy there because I only gave you the average part, and then there's some W's. Okay. Now, so what are they for har? Okay, can I just draw? So har on 0, 1, the scaling function phi is the box. And the wavelet function for har is the alternating box. I'm telling you those in advance of saying what these mean or where they come from or anything. So I'm quite guilty here. But so the idea will be, here's the idea. I want to represent any function. How? What are my basis functions? I'm getting to this word basis. What are my basis functions with har? Okay. What are my basis functions? My basis functions are this box and its shifts. So all the phi of x or t, I'm usually using t, and its shifts. Do you realize that if I graph phi of t minus 2, here's the graph of phi of t here. What's the graph of phi of t minus 2, just so we pin down the role of this of that index? It's between 2 and 3, right. Here was between 0 and 1. If k is 2, then it shifts it over 2. If k is 1, it shifts it over 1. What I've got now here, and if I take their combinations, what have I got in this bit? What kind of a function is that? It's a steppy function. It's a, well, if we really gave an accurate description, it's piecewise constant. And where are the breaks? At the integers. It's a function that's steppy. Okay. Now I'm going to use, what kind of a function have I got with these w's? Now let me put in some bk's, w at t minus k. What have I got out of those? I maybe should have made that yellow. W at t minus k. With this w, what is that going to contribute? Well, let me just look over the interval 0, 1. If I combine some multiple of this guy and some multiple of this guy, what can I produce? It would be, what will I get out of that? I could get any, it'll have jumps at a half, right? We're really at multi-resolution here. We're right on the center of idea here. That if I combine some multiple of this and some multiple of this, what can I get? I can get, it'll be piecewise constant, certainly, in that half and that half. But I can adjust it to be anything. I got a two-dimensional space. I got one dimension by the average and one dimension by the difference. It's, right? I could combine maybe, some multiple of this, say one of that and two of that, then combining those would give me something that went up to 3 and down to -1 or something. Right? This tells me the average, and this tells me the detail, which was the har idea, right? So for functions This is, those are the two functions that correspond perfectly to Haar, that tell me the average and the details. Now, suppose my function isn't that, but suppose my function has got more detail in it. Suppose my real function has details, let's say it's got more details. This is still 0, 1. But suppose that guy. How could I produce that function? I need another, what do I need here? Wait a minute. How many? I need another scale. And how many functions at that scale? It won't do if I just, I keep this scale, which will tell me the average. So with some white dot, I would, some average. That's my contribution from this function, and then something from this function. But now, how many more functions, and what function shall I have?
You need more than one in several positions.
That's right. I'm going to need, exactly. I'll need, going from 0 to 1 still, I'll want somebody who's happy on just that half, right? So this is just up to a half. And then I think I need a fourth guy. I think this has 4 degrees of freedom. So I better have 4 basis functions. And what should be my other basis function? Shift this guy. So that's what these, now I'm going to put in 2 to the j there. So j equals 0 gave me this. This was j equals 0. This is j equal 1, k equals 0. No shift. And then the fourth guy that you're just telling me I get it up there is the same, 0 to 1, but it's the wavelet on this second half. And that's j equal 1, half scale, and k equal 1, shift 1 shift. Do you see that I'm up to 2 indices here? A j that tells me the scale, and a k that tells me the position. I think this is really worth thinking about. And now suppose, let me jump. All right, I'll jump. I'll take only one more jump, and then I'll take an infinite jump. Okay, suppose my function is like that, like a staircase. What scale am I on? What basis function should I be using to reproduce that perfectly? I want to keep these. The great idea of multi-resolution, it's hierarchical. These guys still contribute. There's 4 of those. How many more do I need? I need what? Another 4?
No,
Because I've got 8. Yeah, I've got 8 numbers here.
yeah, but doesn't your first one plus some more than just increment goes along?
Yeah, I think what I'm going to need is the next level will be a j equal to 2. So 2 to the j would be 4 then. So that's got me to this 1/4 scale. And then I think k could be 0, 1, 2, or 3. It's these guys. And there's a b, j, k, and there I've broken the bank here. I've got at the basic scale, I've got the scaling function and it shifts. At the basic scale and all the other scales, I've got the wavelet and it shifts. So I've got whole lots of details. That's what was. Remember, my filter bank had detail, 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 and then one average guy to pull it together.
Your base function doesn't split the same way that the wavelet
I don't split the base function. Right, the phi. That's right. Yes. Yes, I don't split the base function. Now, what I'm going to say, and I'm not going to achieve it today, is, well, I said that these two functions were the phi, this was the phi, and this was the w for the Haar filter bank. Somehow this phi is associated with the particular numbers 1/2, 1/2. It comes from those numbers by some magic equation to be seen. And this comes from the numbers 1/2 minus 1/2 in a magic way. What am I trying to say? That if you give me another filter pair, like 5, 3, there's some associated with that is some phi of t and some w of t. And phi of t somehow reflects the low pass part, and w reflects the high pass part. But reflects also the infinite number of iterations that are going to enter when we're dealing with functions. Did we see that we really needed to get an actual straight line? Do you see that I'll need all scales? I was able to get this scale with getting this staircase with j equals 0, 1, and 2. But then if I want to have a finer staircase, I need j equals 3. And the limit, when I really want to just say, okay, suppose my signal is steadily increasing, then I'm going to need all those scales. And I could produce the signal out of that. I'm kind of making that jump into continuous time where you're asking me to reproduce a function, so you have to allow me infinitely many basis functions to do it. It's like the DFT. If I have an 8-point DFT, you give me 8 basis functions, I've got it. But if you give me a function of time and say, produce that exactly, you have to give me an infinite family of, an infinite basis to get it right. So this will be the infinite basis, the function and all its, the scaling function and its shifts, and the wavelet function and its shifts and its rescalings. So it's a kind of an unusual basis. It's got these two aspects, the phis and the w's to it. Right. Right. Yeah. I feel we've covered quite a bit. Are we maybe at a pause point? Because I have more to say about multi-resolution, where these functions come from. I mean, the point is, they're associated with filters. That's the magic of this subject, is that if you give me those filters that we constructed, they lead to functions phi and w that work in continuous time. And quite remarkable functions. Oh, well, allow me to write down the equation for phi, just so I've written it down. It's the fundamental equation of the whole subject, of the wavelet subject. I mean, you could do filter banks without it. The FBI happily implemented the 9-7 filter bank, but the reason it was good had something to do with the scaling function, phi of t. So here's its equation. Yeah, I can't resist telling it to you. So it involves the low-pass coefficients, and the scaling function appears here, but downsampled, so there's a 2t, and so this is like, there's a downsampling and a convolution, and that does it. And then maybe I need a factor 2 there to normalize it. There's an amazing equation, deserving of our attention next time. Can I let's just think a little bit about that equation. let's see. Example is har. Then my equation becomes what? Phi of t is 2 times, what are the har coefficients? The low-pass har coefficients are 1/2 and 1/2. So they multiply the 2 to give 1 and 1. So I have phi of 2t and phi of 2t minus 1. That's the har example. So this is the famous equation that gives the scaling function for har and in general. And would you like to tell me the solution to that equation? We just saw it, right? It's the box. Would you like to tell me the solution to that equation? No. Right. It's fantastic. Look, it's a constant coefficient equation. It involves shifts. I mean, what more could you ask? But it does involve this 2 scales, 2t and t. And that changes everything. That really makes that constant coefficient linear. If I could take the Fourier transform of that equation, you think, oh boy, that can't be that hard. But the 2 scales makes it different features entirely. In this case, we can guess the answer and check it, and it is the box, because this is the first half box and this is the second half box, and the 2 half boxes add up to the box. Fine. Would you like to, how about the 1, 2, 1? Would you like to guess? So next example. So the coefficients are 1, 2, 1, coming from the 5, 3, coming from the 3. This is my final, guaranteed final thing. Okay, so 1, 2, 1, I divide by 4 to make them add to 1, and I multiply by 2. So phi of t, so this is example 2. Phi of t is, so 2 times 1/4, 1/2, phi of 2t, and 2 times 2/4 is 1, phi of 2t minus 1, and 1/2 phi of 2t minus 2. All right. I could leave that as a challenge. I'm inclined to say we worked hard today, and we reached, at least I've written down the equation for the scaling function, which, and just said, this is an amazing equation to deal with. And one example we certainly could deal with, and I think you could possibly guess the answer to that one, or find it somehow. Can I, is that fair? So that's like the homework problem, to solve that equation somehow. You could take Fourier transform if you like, you could iterate if you like, you could look in the book if you like. You could connect it somehow to this equation. That's not so obvious. But one way or another, let me start with that example and then move back to the big picture. But remember, this function was associated with the filter with the filter 1, 2, 1, or 1, 2, 1 divided by 4. Is that fair for a challenge for next Thursday? So I'll still be going on filter banks, the reasons for zeros at pi, and the applications. I mean, today's lecture threw us into the construction of filter banks that were invertible and finite length without a lot of why are we doing this? And so let me try to add some of that in the next lecture. Why is this whole new world, what does it have to contribute signal processing. Okay, so for next Thursday, we've got some more about wavelets. And then the final days will be about optimization, simplex method, linear programming, other interesting developments. Thanks.